Hello, in the practical exam papers, we are often asked to validify a suggested relationship. And these kind of questions actually come in two different formats. In the first format, you'll be asked to collect at least 6 sets of data. You're going to plot a graph using these 6 sets of data. And from the graph, you validify the relationship. In the second format, you'll be asked to collect only 2 sets of data. And based on just these 2 sets of data, without plotting any graph, you'll be asked to validify the relationship. So this video is about this kind of questions. How to validify a relationship using just 2 sets of data. So here is one example. This is the suggested relationship. H equals to CD squared. So C is a constant. And the question in the earlier parts have asked you to collect 2 sets of H and D data. Let's take a look, yeah? So right at the beginning of the question, you're asked to measure D and then measure H. So this is the first set of H and D data. Later on, you'll be asked to collect a second set of D and H data. So based on these 2 sets of data, how do we conclude whether this relationship is valid or not? The obvious thing to do is to calculate the constant C, isn't it? So C is equals to H over D squared. And since we have 2 sets of H and D data, we can calculate 2 values for the constant C. So the first one is calculated using the first set of H and D data, and the second value of C is calculated using the second set of values for H and D. And we end up with these 2 values of C. Now in theory, these 2 numbers should be exactly the same, because if the relationship is valid, C ought to be a constant. But due to experimental uncertainties, of course, we shouldn't be surprised if these 2 numbers are not exactly the same. So basically, we have to decide whether the difference is so big that we have to reject the suggested relationship, or are we going to conclude that the difference is small enough for us to accept this relationship. So how big is too big and how small is too small? Obviously, we shouldn't be looking at the absolute difference. We should be looking at the percentage difference. So calculate the difference in the 2 C values divided by the first value. We obtain a percentage of 16.7%. Now the tendency is for students to say, wow, 16.7%, that's a very big difference, you know. Maybe they'll write something like, oh, since the difference is larger than 10%, I'm going to reject the relationship. You're going to lose the mark. Now, you're not supposed to use your own arbitrarily chosen threshold value. And so you ask, if not, then what? Now, for such questions, there's always an earlier part where you're asked to estimate some percentage uncertainties. Let's look for it in this question, yeah? So let's move to the earlier parts. See here, in this part here, you're asked to estimate the percentage uncertainty in your value of H. H, what is H? See, in this experiment, you're supposed to keep lengthening H until the ball droops down, yeah? Until the ball droops down like that. And if you have done this experiment, you know that this value of H is actually very subjective, yeah? It's prone to a lot of random errors. And in fact, when you measure it yourself, you may realize that there's a range of values. And that's why the question asked you to estimate the percentage uncertainty. And so for this part here, we know a lot of students, those who never listen to teachers in class, for this part, they tend to write down 0.1 cm, or they write down the resolution of the instrument because it was a meter rule, right? So a lot of students will write down 0.1 to be the absolute uncertainty, and then they'll lose the mark. Now, the reason Cambridge asks you this part is because they want to test you whether you're aware that besides instrumental uncertainty, there's also this thing called the procedural uncertainty. So even though the meter rule gives you a precision of 0.1 cm, you can see that our uncertainty in the true value of H is actually more than 0.1 cm. It's more than the resolution of the instrument. So the uncertainty in this measurement is not caused by the resolution of the instrument. It's caused by the nature of this measurement. Sometimes the wire droops down earlier, sometimes it droops down later for some random reason. So if you're aware of this, then you know that you must not write the resolution of the instrument as your uncertainty. So just use your gut feel and write down an uncertainty that's more than the resolution of the instrument. From experience, we know that if you write something that's between 2 to 5 times the resolution of the instrument, you'll be okay. Meaning you should write down something that's between, say, 0.2 to 0.5. The other thing is, this absolute uncertainty must always be expressed to 1 SF only. Meaning if instead of 0.3, you go and write 0.32, you're going to lose the mark. Because by writing 0.32, you're telling everyone that you're not aware that this is just an estimate. An estimate deserves only 1 SF. So you should write down either 0.2, 0.3, 0.4 or 0.5. You mustn't write 0.1 because that's only the resolution of the instrument, and you're telling everyone that you're not aware that there's such a thing as procedural uncertainty. And you also shouldn't write something like 0.29, because then you're not writing it to 1 SF and you're telling everyone that you're not aware that this is an estimate that deserves only 1 SF. So let's say we write 0.3, alright, and then we calculate the percentage uncertainty in age to be 3.5%. Now, how do we make use of this number? Let's go back to the part where we're asked to validify the relationship. So we calculated C using H over D squared, right? That means the percentage uncertainty of C is actually equals to the percentage uncertainty of H plus 2 times the percentage uncertainty of D. So you actually have to make use of what you learned from chapter 1, yeah? How to propagate uncertainties in the calculations. Now, the percentage uncertainty of H, we have estimated it to be 3.5%, right, earlier. So this 3.5% is going to be the magic number, the threshold we use to conclude whether this percentage difference is too big or too small. So for this example here, we are going to say that since C differ by 16.7%, which is more than the 3.5% uncertainty of H, the relationship is not supported. Get it? You do not use your own arbitrary threshold value. You use some estimated percentage uncertainty that you have been asked to estimate earlier in the question. And in fact, you must explicitly write down that number in your answer here. Now, many students are going to ask, what about delta D over D? Now, if you are a very strong student, you can go ahead and estimate this as well and incorporate this as your threshold value. But then, if the question didn't make you do the estimate earlier, usually it's because this is a very simple measurement and the percentage uncertainty is negligible compared to the uncertainty in the value of H. So that's how you play the game, get it? You look for an earlier part where you're made to estimate some percentage uncertainty. For this case, it's just H. And then you use that to decide whether to accept or reject the relationship. Okay, let's look at another example and it'll be clearer after that. So this another question, you're going to do a torsional oscillation of this ruler. And the period of oscillation apparently depends on D, this distance D, the distance between the two strings. It also depends on this distance L, which is the distance between these two rulers. So the question will guide you to collect one full set of data. So see, D is measured here, L is measured here, and then the period also measured here. So that's one set of D, L, and T data. And then you'll be asked to measure a second set of D, L, and T data. Next, they will propose the relationship here. So using those two sets of D, L, and T data, you can calculate two values of K. So these two values are not exactly the same, no surprise, yeah? This is an experiment, it has practical uncertainties. So we go ahead and calculate the percentage difference. Turns out to be only 0.885%. So please don't go and write, oh, since it's less than 1%, it's such a tiny difference, the relationship must be correct. Don't use your own arbitrary threshold value. Instead, you got to figure out what is the acceptable difference in the values of K. So earlier in the question must have made you make some estimate uncertainties, either in T, D, or L. So let's look at the earlier parts of the question. See here? Estimate the percentage uncertainty in your value of D. So D is 40.0%, but what is its uncertainty? So see here, you mustn't write 0.1 here, yeah? 0.1 cm is the resolution of the ruler, but if you write the resolution of the instrument as the absolute uncertainty, the market will say, oh, this student is not aware of procedural uncertainty. So like I said, you can write something that's between 2 times and 5 times the resolution of the instrument. So 0.2 is good, 0.3 is good, 0.4 is good, 0.5 is good. Don't write something that's too big, like 1 cm, 2 cm, yeah? I mean, if you want to write something like 5 cm, you better be very confident of it, because 5 cm out of 40 cm, there's like 12.5% uncertainty. Usually, such crappy measurements do not appear in an exam paper. And the other thing is, remember, you must write this to 1 SF, yeah? So please don't write numbers like 0.25. So here we have the percentage uncertainty of D. Let's check the other parts of the paper. See here? You are made to estimate the percentage uncertainty of L. So again, don't write 0.1, yeah? I write 0.4 here. Why? Because you can see this measurement of L is actually more problematic than the measurement of D. Because it's not easy, yeah, to make sure the distance between these two rulers is always constant. It's not easy to hang two rulers perfectly horizontally, especially this one. So because of that, I think this deserves a larger uncertainty. That's right. That's why I write 0.4 here. And remember, 1 SF, yeah? Don't write 0.40. This number must be expressed to 1 SF only. So is a 1.5%. So remember, yeah, delta D over D was 0.5%. Delta L over L is 1.5%. So let's go back to this part here. So delta D over D is 0.5%. Delta L over L is 1.5%. What about delta T over T? The question didn't ask us to make an estimate of it. Reason is because this measurement of T only has a tiny percentage uncertainty. So now you can go ahead and say that since our values of K differ by 0.885%, which is smaller than this amount. Where did this amount come from? 2 delta D over D plus delta L over L. So 0.885% is smaller than this 3.5%. So you must explicitly show this working, yeah? You must always explicitly show the two numbers that you are comparing. So since this is smaller than this, the relationship is supported. So this is how the game is played, get it? So two sets of data, two values of the constant, calculate the percentage uncertainties, and then look for the earlier parts in the question where you are asked to make some estimates of percentage uncertainties. Make sure you write this to 1SF. Make sure you don't write the resolution of the instrument here. Our suggestion is to write something that's between 2 to 5 times the resolution of the instrument. But of course, you use your own judgment. I cannot guarantee that Cambridge is not going to throw a curveball at you. So you decide for yourself. But whatever you decide on, make sure you write it to 1SF and make sure it's more than the resolution of the instrument. So after that, based on the experimental uncertainties, you decide whether the actual difference in the values of K falls within the range of experimental uncertainties, and from there you conclude whether the relationship is valid or not. Alright, that's all. Ta-ta!